Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you've found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the invisible dance between a wandering comet and Earth's magnetic embrace. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. In the vast darkness beyond Neptune's orbit, something ancient stirs. The interstellar comet 3I Atlas, a visitor from another star system entirely, continues its lonely journey through our solar neighborhood. This wanderer carries within its frozen heart the chemical fingerprints of stellar processes that occurred long before our sun ignited. The nucleus, perhaps 2 kilometers across, holds secrets from a stellar nursery that existed when our own solar system was nothing more than a collapsing cloud of gas and dust. As it drifts closer to our star, the comet's surface begins to respond to solar radiation with the patience of geological time. The warming happens gradually, almost imperceptibly, like the first breath of spring touching winter ice. Solar photons, having traveled 93 million miles from the sun's surface, finally encounter this ancient ice for the first time in perhaps millions of years. The interaction is gentle, persistent, inevitable. Water ice sublimates directly into vapor without melting, creating a thin atmosphere around the comet's nucleus. This coma expands slowly, methodically, like morning mist rising from a quiet lake at dawn. The process follows the inverse square law as distance to the sun decreases. Solar heating increases exponentially. At 5 astronomical units from our star, the comet receives 25 times more energy than it did at the orbit of Pluto. Yet even this dramatic increase unfolds with cosmic slowness. Carbon monoxide and carbon dioxide join the water vapor in this ethereal dance, released from depths where they have waited in crystalline patience. These molecules, frozen solid at temperatures approaching absolute zero, now taste sunlight for the first time since their parent star died billions of years ago. Each sublimating ice crystal carries isotopic ratios that speak of stellar nucleosynthesis in alien suns, of supernovae that scattered heavy elements across the galaxy before our solar system even existed. The comet's rotation period, measured at approximately 16 hours, creates subtle variations in the sublimation rate. As different regions of the nucleus face the sun, jets of vapor emerge from specific locations on the surface. These jets are not random. They follow the comet's topography, emerging from depressions and valleys where volatile materials have accumulated over cosmic time. The resulting coma develops an asymmetric structure, slightly elongated in the direction opposite the sun. Scientists estimate that 3I Atlas originated in the Oort cloud of another star system, perhaps ejected during a close stellar encounter eons ago. The mathematics of such events are well understood when 2 stars pass within a few light years of each other. Their gravitational fields can disturb the outermost comets in each system's Oort cloud. Some comets fall inward toward their parent star, while others are flung outward into interstellar space at velocities exceeding the escape velocity of their birth system. The precise mechanics of 3I Atlas's arrival in our solar system remain beautifully uncertain. Did a passing red dwarf star, perhaps Proxima Centauri during an earlier epoch, disturb its original orbit through gravitational perturbation? Was it nudged by the gravitational influence of a massive planet orbiting its parent star, a world we cannot detect across the light years? Or did the death throes of its parent star itself provide the initial impulse that sent this frozen wanderer into the darkness between stars? These questions linger in the astronomical literature like unsolved poems, mathematical elegance without final answers. The comet's trajectory through our solar system follows a hyperbolic path, indicating its interstellar origin with mathematical certainty. Its orbital eccentricity exceeds unity, meaning it will never return once it departs. This is a one-time encounter, a cosmic handshake between our Sun and a messenger from distant stellar shores. The gravitational influence of Jupiter and Saturn will slightly modify its path, adding our solar system's signature to its trajectory as it continues toward interstellar space. Spectroscopic analysis reveals water vapor, carbon monoxide, and traces of organic compounds in the expanding coma. These measurements, taken by ground-based telescopes and space-based observatories, provide the first chemical census of material from another stellar system. The deuterium-to-hydrogen ratio in the water vapor differs slightly from that found in Earth's oceans, confirming the comet's foreign origin. Each photon of reflected sunlight carries information about molecular bonds formed in stellar environments unlike our own. Only took 4.5 billion years to reach us. Only traveled perhaps 25 trillion kilometers through the cosmic dark to arrive at this moment. Only needed to survive the absolute cold of interstellar space, the bombardment of cosmic rays, and the gravitational perturbations of passing stars to deliver its quiet message to our instruments. The probability of such an encounter seems impossibly small, yet here the ancient wanderer drifts, patient as geology, inevitable as mathematics. The comet bears no awareness of the electromagnetic drama it is about to initiate, no knowledge of the planet ahead, whose magnetic field will soon taste the essence of distant stellar winds. It simply exists, following the gravitational choreography of celestial mechanics, transforming slowly from pristine ice to expanding gas as our star's energy penetrates layers that have remained frozen since the youth of the galaxy. In its gradual awakening, 3i Atlas prepares to participate in an electromagnetic conversation with Earth's magnetosphere, a dialogue between worlds separated by both space and deep time. The solar wind begins its journey in the Sun's corona, where temperatures reach 2 million degrees Celsius, and the plasma becomes so energized that our star cannot contain it. Protons and electrons, liberated from their atomic bonds by extreme heat, stream outward at velocities approaching 400 kilometers per second. This invisible river of charged particles carries with it the magnetic field lines of the Sun itself, stretching and distorting them into vast spirals that extend far beyond the orbit of Pluto. At the distance of Earth's orbit, the solar wind maintains a density of approximately 5 particles per cubic centimeter, a vacuum more complete than anything achievable in terrestrial laboratories, yet dense enough to carry electromagnetic influence across the solar system. These particles, mostly hydrogen nuclei stripped of their electrons, have traveled for 4 days from the Sun's surface before reaching our planet's neighborhood. Each proton carries kinetic energy equivalent to its motion through space, while electrons dance in complex helical patterns around the magnetic field lines. The wind structure reveals itself in layers and variations, fast streams, originating from coronal holes where the Sun's magnetic field opens to space, race outward at speeds exceeding 800 kilometers per second. Slow streams, emerging from the Sun's equatorial regions, maintain more sedate velocities around 300 kilometers per second. When fast streams overtake slow streams, they create compression region zones of enhanced density and magnetic field strength that sweep through the solar system like invisible waves. Embedded within this flow are the remnants of solar storms, coronal mass ejections that erupted from the Sun's surface days or weeks earlier. These magnetic clouds carry field orientations that may oppose Earth's magnetic field, setting the stage for powerful geomagnetic storms when they arrive. The interplanetary magnetic field, carried outward by the solar wind, rotates with the Sun's 27-day period, creating a vast spiral pattern known as the Parker spiral after the physicist who first described its geometry. The solar wind's magnetic field strength at Earth's orbital distance averages about 5 nanotesla, roughly 10,000 times weaker than a typical refrigerator magnet, yet sufficient to carry electromagnetic information across planetary distances. This field connects every planet in the solar system to the Sun's magnetic influence, creating what space physicists call the heliosphere, a vast bubble of solar influence extending perhaps 100 astronomical units into interstellar space. Between Mercury and Mars, the solar wind encounters no significant obstacles. Venus, lacking a global magnetic field, offers little resistance to the solar wind's advance. Mars, with only weak crustal magnetic fields remaining from its ancient dynamo, presents minimal deflection. Earth stands unique among the inner planets in possessing a strong, active magnetic field capable of creating a substantial impediment to the solar wind's progress. Scientists have wondered for decades about the precise mechanisms that accelerate the corona to such extreme velocities. The solar wind's existence was predicted theoretically by Eugene Parker in 1958, but the detailed physics of coronal heating and wind acceleration remain areas of active research. Magnetic reconnection events, wave heating, and turbulent dissipation all contribute to the process, yet no single mechanism fully explains the observed temperatures and velocities. Only took the Sun 4 billion years to perfect this stellar exhalation. Only required the gravitational collapse of a primordial gas cloud, nuclear ignition, and billions of years of magnetic dynamo action to establish this constant outflow. Only needed to convert 4 million tons of matter into energy every second to maintain the pressure gradients that drive the solar wind's eternal journey outward through space. As 3I Atlas approaches the inner solar system, it encounters this invisible ocean of charged particles for the first time in its interstellar wandering. The comet's expanding coma, now stretching thousands of kilometers around its nucleus, begins to interact with the solar wind's magnetic field lines. Water molecules, dissociated by solar ultraviolet radiation, create hydrogen and oxygen ions that become entrained in the wind's flow. The interaction starts subtly. Individual molecules sublimating from the comet's surface become ionized by solar extreme ultraviolet radiation, losing electrons and acquiring positive charge. These newly created ions, still moving with the comet's orbital velocity, encounter the solar wind's magnetic field. The Lorentz force, acting on charged particles in motion through magnetic fields, begins to deflect these ions away from their original trajectories. A bow wave begins to form upstream of the comet as the solar wind encounters the expanding cloud of neutral gas and newly formed ions. This is not yet the dramatic bow shock that forms around planets with strong magnetic fields, but rather a gentler disturbance, a subtle modification of the wind's flow pattern as it accommodates the comet's presence. The solar wind, accustomed to traveling unimpeded through interplanetary space, must now navigate around an expanding obstacle of gas and dust. The comet's tail begins to take shape. Not yet the spectacular appendage visible in telescope images, but rather the first stirrings of plasma acceleration away from the nucleus. Ions formed in the inner coma experience the full force of the solar wind's electromagnetic field accelerating them to speeds matching the wind itself. This creates a faint plasma tail extending opposite the sun's direction, invisible to human eyes but detectable by sensitive spectrographs that can measure the Doppler shift of ion emission lines. The solar wind carries these comet ions away into the outer solar system, incorporating alien chemistry into the heliospheric plasma. Material that originated in another star system now mixes with the sun's own stellar wind, creating a dilute but detectable signature of interstellar matter distributed throughout our local cosmic environment. The comet has begun to exhale its ancient substance into the solar wind's embrace, preparing for the more dramatic electromagnetic encounters that await as it continues its approach toward the inner planets. Deep beneath Earth's surface, 3,000 kilometers down, where pressures exceed those found at the bottom of the deepest ocean trenches, liquid iron churns in the planet's outer core. This metallic ocean, heated to temperatures rivaling the sun's surface, moves in vast convective currents driven by the gradual cooling of Earth's interior and the crystallization of the inner core. As this conducting fluid flows through the weak magnetic field that permeates space, it generates electrical currents that amplify and sustain Earth's magnetic field through a process known as the geodynamo. The magnetic field lines emerge from the southern magnetic pole, arch high above the planet's surface, and converge again at the northern magnetic pole, creating a vast dipolar structure that extends tens of thousands of kilometers into space. This magnetosphere, the region where Earth's magnetic field dominates over the interplanetary magnetic field, forms an invisible shield around our planet, deflecting most of the solar wind's charged particles away from the atmosphere and surface below. The magnetosphere's shape reflects the constant pressure of the solar wind against its outer boundary. On the day side, facing the sun, the magnetic field lines are compressed to a distance of approximately 10 Earth radii. On the night side, away from the solar wind's direct pressure, the field lines stretch into a long magneto tail extending more than 100 Earth radii into space. This asymmetric structure creates a teardrop shape, like a cosmic windsock indicating the direction of the solar wind's flow. Within this magnetic cocoon, charged particles follow complex trajectories governed by the Lorentz force. Electrons and protons spiral along magnetic field lines, bouncing between the northern and southern hemispheres in motions that can take seconds to minutes to complete. Some particles become trapped in the Van Allen radiation belts, toroidal regions of enhanced particle density that encircle the Earth at altitudes between 1,000 and 60,000 kilometers. The magnetosphere's boundary layers reveal the complexity of space plasma physics. The magnetopores, the outermost boundary where solar wind pressure balances magnetic pressure, fluctuates continuously as variations in solar wind density and velocity alter the force balance. Inside this boundary lies the magnetosheath, a turbulent region where solar wind plasma has been decelerated and heated by its passage through the bow shock that forms upstream of the magnetosphere. Earth's magnetic field strength varies across the planet's surface, ranging from about 25 microtesla near the magnetic equator to 65 microtesla near the magnetic poles. This variation reflects the dipolar nature of the field and the 11-degree offset between the magnetic and geographic poles. The magnetic North Pole currently wanders across the Canadian Arctic at a rate of approximately 55 kilometers per year, following complex patterns driven by changes in the core's fluid motion. Scientists have traced the history of Earth's magnetic field through paleomagnetic studies of ancient rocks and sediments. The field has reversed its polarity hundreds of times throughout Earth's history, with the most recent reversal occurring approximately 780,000 years ago. During these reversals, which can take thousands of years to complete, the magnetic field strength drops to about 10% of its normal value, potentially allowing increased cosmic ray bombardment of the atmosphere. The geodynamo's precise mechanism remains one of Earth science's most challenging problems. Computer simulations of core convection require enormous computational resources and still cannot fully reproduce all observed features of the magnetic field. The interaction between thermal and compositional convection, the role of the inner core's growth, and the effects of precession and tidal forces all contribute to the dynamo's operation in ways that are not yet completely understood. Only took 4.5 billion years for Earth to develop this protective electromagnetic embrace. Only required the differentiation of heavy elements toward the center, the establishment of core convection, and the precise balance of thermal and rotational forces to create a self-sustaining magnetic dynamo. Only needed the fortuitous combination of a liquid outer core and a solid inner core to generate the complex field geometry that shields life from the harsh realities of space weather. The magnetosphere responds to external influences with the sensitivity of a vast electromagnetic instrument. Changes in solar wind pressure cause the magnetopores to move inward or outward, compressing or expanding the entire magnetic cavity. Variations in the interplanetary magnetic field orientation can trigger magnetic reconnection events at the magnetopores, allowing solar wind energy to penetrate deep into the magnetosphere and powering geomagnetic storms. During quiet periods, the magnetosphere maintains a relatively stable configuration, with well-defined current systems flowing along the magnetopores and within the magnetotail. The ring current, a westward flowing current of energetic particles encircling Earth at distances of 3 to 7 Earth radii, creates a small but measurable depression in the planet's surface magnetic field. This current intensifies during geomagnetic storms, causing the distinctive decrease in horizontal magnetic field strength that ground-based magnetometers record as the Storm Time Deist Index. The aurora borealis and aurora australis provide visible evidence of the magnetosphere's interaction with solar wind particles. When magnetic reconnection in the magnetotail accelerates particles earthward along magnetic field lines, these particles collide with atmospheric gases at altitudes between 100 and 400 kilometers. Oxygen atoms emit green light at 550.7 nanometers when excited by electron impact, while nitrogen molecules produce blue and red emissions that paint the polar skies in shifting curtains of color. As 3Y Atlas continues its approach toward the inner solar system, its expanding coma and developing plasma tail will soon encounter this vast magnetic structure surrounding Earth. The comet's ionized gases, already entrained in the solar wind's flow, carry electromagnetic signatures that will test the magnetosphere's response to foreign plasma chemistry. The ancient ice, now transformed into charged particles streaming away from the comet's nucleus, prepares to engage in an electromagnetic dialogue with Earth's protective magnetic embrace, a conversation between terrestrial geophysics and interstellar chemistry that will unfold across the vast scales of space plasma physics. As 3I Atlas draws closer to the Sun, crossing the orbital distance of Jupiter, the increasing intensity of solar radiation begins to transform the comet's tenuous coma into something far more dynamic. The process unfolds with glacial patience, yet each passing hour brings measurable changes to the comet's electromagnetic environment. Water molecules, liberated from the nucleus through sublimation, drift outward at velocities of several hundred meters per second, creating an expanding sphere of neutral gas that grows larger with each orbit around the Sun. Solar ultraviolet radiation, particularly the extreme ultraviolet photons with wavelengths shorter than 100 nanometers, carry sufficient energy to ionize these water molecules through photoionization. Each photon collision strips away an electron, transforming neutral H2O into positively charged H2O plus ions that immediately become subject to electromagnetic forces. The ionization rate increases dramatically as the comet approaches perihelion, with the cross-section for photoionization scaling inversely with the square of the distance to the Sun. The newly formed ions retain the orbital velocity of their parent molecules initially, but the Lorentz force, the fundamental electromagnetic force acting on charged particles in motion through magnetic fields, begins to accelerate them in directions perpendicular to both their velocity and the local magnetic field. This creates a complex choreography of particle motion as ions spiral around magnetic field lines carried outward by the solar wind, their trajectories becoming increasingly stretched and distorted. Electron impact ionization adds another layer of complexity to the process. High-energy electrons in the solar wind, with energies exceeding the ionization potential of water molecules, create additional ions through direct collision. This secondary ionization process becomes particularly important in regions where the solar wind's electron temperature is elevated, such as within magnetic clouds or compression regions swept up by fast solar wind streams. The comet's plasma tail begins to take definitive shape as these processes accelerate. Unlike the dust tail, which follows the comet's orbital path and curves gently away from the Sun due to radiation pressure on solid particles, the plasma tail extends almost directly away from the Sun, guided by the magnetic field lines embedded in the solar wind. This plasma tail can extend for millions of kilometers, though its density remains extraordinarily low, perhaps 1,000 ions per cubic centimeter, comparable to a good laboratory vacuum. The tail structure reveals itself in filamentary patterns visible to sensitive spectrographs that can detect the emission lines of ionized gases. Carbon monoxide ions emit strongly at wavelengths around 427 nanometers, while water group ions produce emissions across a broader spectrum. These spectral signatures provide astronomers with a remote sensing capability, allowing them to measure ion densities, temperatures, and velocities from ground-based observatories millions of kilometers away. Magnetic draping occurs as the solar wind's field lines encounter the expanding coma of neutral gas. The interplanetary magnetic field, unable to penetrate regions of high neutral density, becomes draped around the comet's nucleus like invisible cloth flowing around an obstacle. This creates a complex magnetic field geometry where field lines pile up on the upstream side of the coma and stretch into long, twisted configurations downstream. The plasma tail's brightness varies with solar wind conditions and the comet's gas production rate. During periods of enhanced solar wind density or velocity, the increased ion production and acceleration create more prominent tail structures. Conversely, when the interplanetary magnetic field orientation is unfavorable for efficient ion pickup, the tail may appear fainter or less well-defined in telescopic observations. Scientists have identified several distinct regions within the comet's plasma environment. The inner coma, extending perhaps 10,000 kilometers from the nucleus, contains mostly neutral molecules with a small fraction of newly formed ions. The outer coma, stretching to hundreds of thousands of kilometers, shows increasing ion fractions as photoionization and electron impact ionization transform the neutral gas. The plasma tail itself represents the final stage of this transformation, where ions have been fully accelerated to solar wind velocities. Only took solar radiation 8 minutes to travel from the Sun's surface to begin this transformation. Only needed photons with energies of 12.6 electron volts to strip electrons from water molecules and initiate the ionization cascade. Only required the precise electromagnetic choreography of solar wind magnetic fields to organize these scattered ions into the coherent structure of a plasma tail streaming across millions of kilometers of space. The comet's rotation, with its 16-hour period, creates temporal variations in the ion production rate as different regions of the nucleus face the Sun. Active areas, where subsurface ice lies close to the surface, produce jets of vapor that create dense regions within the coma. These jets, detected through high-resolution imaging and spectroscopy, show how the comet's topography and internal structure influence the development of its plasma environment. As the ions accelerate away from the nucleus, they carry with them isotopic signatures that reveal the comet's formation environment. The deuterium to hydrogen ratio in water vapor, measured through infrared spectroscopy, differs from that found in Earth's oceans, confirming the comet's origin in a stellar environment with different nucleosynthetic processes. Heavy water molecules, containing deuterium rather than ordinary hydrogen, ionize at slightly different rates and follow subtly different trajectories in the plasma tail. The magnetic field embedded in the plasma tail develops its own dynamic structure. Magnetic reconnection events, where oppositely directed field lines merge and release magnetic energy, can create localized acceleration regions within the tail. These magnetic reconfigurations, occurring on timescales of minutes to hours, contribute to the complex, ever-changing structure of the comet's plasma environment as it continues its approach toward the inner solar system and its eventual encounter with Earth's magnetosphere. The magnetosphere's bow shock stands as Earth's first line of electromagnetic defense, a vast curved surface extending approximately 90,000 kilometers upstream from our planet, where the supersonic solar wind first encounters the obstacle of Earth's magnetic field. This invisible boundary exists in a state of constant motion, expanding and contracting in response to variations in solar wind pressure, like the surface of a soap bubble responding to changing air currents. The shock itself measures only a few hundred kilometers thick, yet within this narrow region, one of the most dramatic transformations in space, physics unfolds continuously. As 3I Atlas approaches the inner solar system, its expanding plasma tail carries ions that have been accelerated to velocities matching the solar wind itself. These foreign particles, bearing the chemical signatures of stellar processes that occurred in distant star systems, become embedded within the solar wind's flow as they stream past Earth's orbital distance. The solar wind, now enriched with this interstellar chemistry, encounters Earth's bow shock with slightly altered composition and electromagnetic properties. The shock formation occurs when the solar wind's supersonic flow traveling at speeds exceeding the local sound speed in the plasma meets the immovable obstacle of Earth's magnetic field. Unable to flow around this electromagnetic barrier as easily as it flows around planets lacking strong magnetic fields, the solar wind undergoes a violent deceleration. Kinetic energy converts to thermal energy, heating the plasma to temperatures exceeding 1 million degrees Celsius, while simultaneously slowing its bulk velocity from 400 kilometers per second to perhaps 100 kilometers per second. The shock's geometry follows the laws of magnetohydrodynamics, creating a paraboloid shape that extends far into the solar wind upstream of Earth. The nose of the shock, directly between Earth and the Sun, typically lies at a distance of 13 to 14 Earth radii, though this distance varies significantly with solar wind dynamic pressure. During periods of high solar wind density or velocity, the shock moves closer to Earth, compressing the entire magnetospheric system and intensifying the electromagnetic interactions within. Particle acceleration occurs naturally at the bow shock through a process known as diffusive shock acceleration. A small fraction of the incoming solar wind protons and electrons undergo multiple interactions with the shock front, bouncing back and forth across the boundary while gaining energy with each crossing. This mechanism can accelerate particles to energies hundreds of times greater than their initial thermal energies, creating a population of energetic particles that contributes to the radiation environment near Earth. The shock's magnetic field structure becomes highly complex as the interplanetary magnetic field encounters this boundary. Field lines become compressed and tangled, creating regions where the magnetic field strength can be 4 to 5 times greater than in the undisturbed solar wind. These compressed field regions store magnetic energy that can be released through magnetic reconnection events, contributing to the dynamic nature of the shock environment. When the plasma tail ions from 3I Atlas first encounter this bow shock, they experience the same violent deceleration and heating as the ambient solar wind particles. However, their different mass-to-charge ratios cause them to respond differently to the electromagnetic fields present at the shock. Heavy ions, such as those formed from carbon monoxide or carbon dioxide molecules, gyrate around magnetic field lines with larger radii than protons, creating distinct spatial distributions in the shocked plasma. The shock exhibits a phenomenon known as reformation, where the shock front periodically steepens and relaxes on timescales of a few minutes. This process reflects the complex interplay between incoming particles and the electromagnetic fields they generate, creating a dynamic boundary that constantly adjusts its structure to maintain the energy balance required for shock formation. High-resolution spacecraft measurements reveal that the shock front contains multiple layers and substructures that evolve continuously. Scientists have identified several types of bow shock depending on the angle between the incoming solar wind and the local magnetic field orientation. Quasi-perpendicular shocks, where the magnetic field lies nearly perpendicular to the shock normal, tend to be more stable and efficient at thermalizing the incoming plasma. Quasi-parallel shocks, where the field lines are more aligned with the shock normal, often exhibit turbulent foreshock regions extending far upstream where reflected particles create electromagnetic waves and instabilities. Only took the solar wind 4 days to travel from the sun before encountering this electromagnetic barrier. Only needed the precise balance of magnetic pressure and plasma pressure to create a boundary capable of deflecting a supersonic flow of charged particles around an entire planet. Only required the complex physics of collisionless plasma shocks to transform the kinetic energy of stellar wind into the thermal energy that heats the magnetosheath to temperatures exceeding those found in stellar coronas. The foreshock region, extending upstream from the bow shock along magnetic field lines connected to the shock surface, becomes populated with particles reflected from the shock front. These reflected ions and electrons create electromagnetic waves that propagate back into the undisturbed solar wind, effectively announcing the presence of Earth's magnetic obstacle to incoming plasma streams. The wave activity in the foreshock can extend tens of thousands of kilometers upstream, creating a complex electromagnetic environment that modifies the solar wind properties before they reach the shock itself. As ions from 3I Atlas's plasma tail encounter these foreshock waves, they experience additional acceleration and scattering that modifies their trajectories before they reach the main shock front. The foreign chemistry of these interstellar particles adds new spectral signatures to the electromagnetic emissions generated in the foreshock region, creating subtle but detectable modifications to the radio and plasma wave environment that sensitive spacecraft instruments can measure. The bow shock's response to the presence of heavy ions from the comet's plasma tail remains subtle but measurable. The additional mass loading slightly reduces the shock's efficiency at thermalizing the incoming flow, while the different charge-to-mass ratios of the comet ions create distinct populations in the downstream magnetosheath region. These effects represent the first electromagnetic signatures of the comet's interaction with Earth's magnetospheric system, a gentle herald of the more complex plasma physics phenomena that will unfold as the interaction intensifies. In the space between the bow shock and the magnetopause, within the turbulent region known as the magnetosheath, magnetic field lines from Earth's magnetosphere and the interplanetary medium approach each other with the inevitability of opposing forces in cosmic tension. When these field lines carry opposite orientations, northward, Earth field, meeting southward, interplanetary field, or vice versa, the conditions become favorable for one of the most fundamental processes in space, plasma physics magnetic reconnection. The field lines, unable to maintain their separation when pressed together by the solar wind's relentless pressure, suddenly snap and reconfigure into new topological arrangements. The reconnection process occurs at the magnetopause, the boundary between Earth's magnetic domain and the solar wind's electromagnetic influence. This boundary, typically located 10 to 12 Earth radii from the planet's center on the day side, fluctuates continuously as solar wind pressure varies and magnetic field orientations change. When reconnection begins, it creates what plasma physicists call an X-line, a narrow region, perhaps only a few hundred kilometers wide, where the magnetic field topology undergoes rapid reorganization. Energy stored in the stressed magnetic field configuration releases explosively during reconnection events, converting magnetic energy into kinetic energy of charged particles. Electrons and ions accelerate away from the reconnection site at velocities that can exceed 1,000 kilometers per second, carrying enormous amounts of energy into both the magnetosphere and back toward the solar wind. The process resembles a cosmic capacitor discharging, releasing energy that has been slowly accumulated as the solar wind compresses Earth's magnetic field. As ions from 3I Atlas's plasma tail reach the magnetopause, they carry with them the magnetic field signature of the interplanetary medium in which they have been traveling. These foreign ions, with their distinct isotopic compositions and charge states, become participants in the reconnection process as the comet-modified solar wind encounters Earth's magnetic barrier. The heavy molecular ions H2O+, CO+, CO2+ behave differently from the simple protons and electrons that typically dominate solar wind composition. The reconnection process creates distinctive plasma jets that accelerate particles along the newly reconfigured magnetic field lines. These jets, observable through their characteristic signatures in particle and field measurements, transport energy and momentum across the magnetopause boundary. When reconnection occurs on the day-side magnetopause, it can inject solar wind plasma directly into the magnetosphere, while night-side reconnection in the magnetotail can expel magnetospheric plasma into the solar wind. The rate of magnetic reconnection depends critically on the orientation of the interplanetary magnetic field relative to Earth's dipolar field. When the interplanetary field points southward, anti-parallel to Earth's northward-pointing field at the day-side magnetopause, reconnection proceeds efficiently and can transfer significant amounts of solar wind energy into the magnetosphere. Northward interplanetary field orientations generally result in much weaker coupling between the solar wind and magnetosphere. Magnetic reconnection exhibits a phenomenon known as bursty reconnection, where the process alternates between periods of rapid energy release and relative quiescence. These bursts, lasting from seconds to minutes, reflect the complex feedback between the reconnection process and the surrounding plasma environment. The newly reconnected field lines can become loaded with plasma, reducing the efficiency of further reconnection until the field lines have been cleared by plasma transport processes. The presence of heavy ions from the comet's plasma tail subtly modifies the reconnection dynamics through their different mass-to-charge ratios. Heavy ions gyrate around magnetic field lines with larger radii than protons, creating distinct spatial scales in the reconnection region. This mass loading effect can reduce the reconnection rate while creating more complex particle acceleration patterns within the reconnection jets. Scientists have observed that the magnetic reconnection process creates its own electromagnetic signatures that propagate throughout the magnetosphere as Alphen waves, low-frequency oscillations that travel along magnetic field lines at the Alphen velocity, typically a few thousand kilometers per second in the magnetospheric environment. These waves can trigger responses in distant regions of the magnetosphere, coupling reconnection events at the magnetopores to phenomena in the radiation belts and ionosphere. Only took magnetic field lines microseconds to reconfigure once the reconnection process began. Only needed the precise alignment of opposing magnetic fields and the presence of sufficient plasma to mediate the electromagnetic interaction. Only required the conversion of magnetic stress energy, accumulated over hours of solar wind compression, into the kinetic energy of accelerated particles streaming away from the reconnection site at supersonic velocities. The dance of magnetic reconnection continues with rhythmic persistence as the orientation of the interplanetary magnetic field varies with the rotation of the Sun and the passage of solar wind structures. Each reconnection event transfers approximately 10 naurant 15 joules of energy from the solar wind to the magnetosphere, equivalent to the energy content of a moderate earthquake, yet occurring in the rarefied plasma environment of near-Earth space, where such enormous energy transfers create barely perceptible disturbances in the terrestrial environment below. As 3U Atlas continues its orbital journey, the flux of heavy ions from its plasma tail provides a continuous supply of foreign chemistry to the reconnection process. These ions, once locked in crystalline ice structures formed in the cold depths of another stellar system, now participate in the electromagnetic choreography of Earth's magnetospheric boundary. Their presence adds new spectral lines to the electromagnetic emissions generated during reconnection, creating subtle but measurable signatures that space-based instruments can detect and analyze. The reconnected magnetic field lines, now carrying a mixture of terrestrial and interstellar plasma, begin their journey through the magnetosphere. Those that reconnect on the dayside magnetopores are swept over the polar regions toward the nightside magnetotail, where they may participate in additional reconnection events that eventually return them to the solar wind. This circulation pattern, driven by the continuous pressure of the solar wind and mediated by magnetic reconnection, creates a vast electromagnetic engine that processes both terrestrial and alien plasma through the complex geometry of Earth's magnetic environment. Encircling Earth at altitudes between 1,000 and 60,000 kilometers, the Van Allen radiation belts contain populations of energetic electrons and protons trapped within the planet's magnetic field. These belts, discovered in 1958 by instruments aboard the first American satellite, exist as invisible toroidal zones where charged particles spiral endlessly around magnetic field lines, bouncing between magnetic mirror points in the northern and southern hemispheres. The inner belt, composed primarily of high-energy protons with energies exceeding 30 million electron volts, remains relatively stable in its particle population and spatial extent. The outer electron belt, however, exhibits remarkable variability, expanding and contracting in response to changing space weather conditions. Electrons in this region, with energies ranging from hundreds of thousands to several million electron volts, can increase in number by factors of 10 to 100 during geomagnetic storms, then decay over periods of days to weeks through interactions with electromagnetic waves and atmospheric losses. This dynamic behavior reflects the complex interplay between particle injection from the magnetotail, local acceleration processes, and loss mechanisms operating throughout the radiation belt environment. As the solar wind carries ions from 3I Atlas's plasma tail past Earth, these foreign particles begin to influence the electromagnetic environment in which the radiation belts exist. The heavy molecular ions, with their distinct charge-to-mass ratios, interact differently with the various wave modes present in the magnetosphere. Ultra-low frequency waves, with periods of several minutes, can resonate with these heavy ions and transport them across magnetic field lines through a process known as radial diffusion. The injection of new particle populations into the radiation belts occurs primarily during periods of enhanced geomagnetic activity, when magnetic reconnection in the magnetotail accelerates particles earthward along magnetic field lines. Some ions from the comet's plasma tail, having been incorporated into the solar wind flow and subsequently processed through magnetospheric circulation, eventually reach the inner magnetosphere, where they can become trapped in the radiation belt environment. Electromagnetic ion cyclotron waves, generated by temperature anisotropies in the plasma, play a crucial role in radiation belt dynamics. These waves, with frequencies ranging from a few tenths to several hertz, can interact resonantly with both electrons and ions, causing particle precipitation into the atmosphere or acceleration to higher energies. The presence of heavy ions from the comet modifies the dispersion properties of these waves, subtly altering their propagation characteristics and their interactions with the resident radiation belt particles. The plasmasphere, a region of cold, dense plasma extending from the ionosphere to altitudes of several Earth radii, provides another medium through which comet-derived ions can influence radiation belt behavior. This co-rotating plasma, composed primarily of hydrogen and helium ions extracted from the ionosphere, exhibits sharp density gradients at its outer boundary known as the plasma pores. Heavy molecular ions from the comet, if they penetrate into the plasmasphere, can modify its density structure and electromagnetic properties. Particle lifetimes in the radiation belts vary dramatically with energy, pitch angle, and magnetic local time. Low-energy particles may survive for only days before being scattered into the loss cone and precipitating into the atmosphere, while the highest energy particles can remain trapped for years or even decades. The addition of heavy ions from the comet's plasma tail introduces new populations with different scattering cross-sections and loss timescales, creating subtle modifications to the overall radiation belt evolution. The South Atlantic anomaly, a region where Earth's magnetic field is significantly weaker than average, allows radiation belt particles to penetrate to lower altitudes above the South Atlantic Ocean. Spacecraft passing through this region experience enhanced radiation doses that can cause temporary malfunctions or long-term degradation of sensitive electronics. Heavy ions from the comet, if they become trapped in radiation belt orbits, contribute additional mass and charge to this hazardous environment. Scientists have identified several distinct mechanisms by which particles gain energy within the radiation belts. Radial diffusion, driven by ultra-low frequency electromagnetic fluctuations, can transport particles inward to regions of stronger magnetic field where their energy increases to conserve the adiabatic invariant associated with their gyrotion around field lines. Local acceleration by chorus waves, electromagnetic emissions with rising frequency tones resembling birdsong, can energize electrons to relativistic speeds through resonant wave-particle interactions. Only took Earth's magnetic field 4.5 billion years to evolve the complex geometry necessary to trap charged particles in stable orbits around the planet. Only needed the precise balance of magnetic forces and particle dynamics to create these invisible storage rings for energetic radiation circling endlessly through the near-Earth space environment. Only required the delicate interplay of injection, acceleration, and loss processes to maintain populations of particles with energy sufficient to penetrate spacecraft shielding and affect astronaut safety. The radiation belts respond to the injection of comet-derived ions with characteristic timescales that depend on the energy and species of the injected particles. Heavy molecular ions, with their larger gyroradii and different resonance conditions, may preferentially populate certain regions of the belt system while avoiding others. Their presence can be detected through mass spectrometric measurements that reveal the isotopic signatures of their interstellar origin, distinguishing them from the terrestrial ions that normally dominate the radiation belt composition. Electromagnetic Whistler waves, generated by lightning in Earth's atmosphere and propagating along magnetic field lines into the magnetosphere, provide another mechanism through which the radiation belts can be influenced by the presence of foreign ions. These waves, with frequencies between a few hundred hertz and several kilohertz, exhibit modified propagation characteristics when heavy ions alter the local plasma composition, potentially affecting their ability to scatter radiation belt electrons into the loss cone. The slow accumulation of heavy ions from 3I Atlas's plasma tail within the radiation belt environment represents a form of chemical contamination of Earth's near-space environment with matter that originated around distant stars. While the quantities involved remain extraordinarily small, perhaps a few kilograms of material distributed throughout the vast volume of the magnetosphere, the electromagnetic effects of these foreign ions provide sensitive traces of magnetospheric circulation and mixing processes that operate on timescales from minutes to months. Above the polar regions, where Earth's magnetic field lines converge and particles from the magnetosphere rain down into the thin upper atmosphere, the aurora borealis and aurora australis paint the night sky in curtains of green, red, and blue light. These ethereal displays result from collisions between energetic electrons and atmospheric gases at altitudes between 90 and 400 kilometers, where the atmosphere becomes thin enough for electromagnetic phenomena to dominate over purely chemical processes. The characteristic green glow, emitted by oxygen atoms at 557.7 nanometers wavelength, appears when electrons with energies around 1000 electron volts strike oxygen atoms and excite them to higher energy states. The auroras patterns reflect the complex electromagnetic structure of the magnetosphere projected down along magnetic field lines onto the ionospheric canvas. Discrete auroral arcs, aligned roughly along magnetic east-west directions, mark the locations where field-aligned currents carry electrons from the magnetosphere into the atmosphere. These currents, with densities reaching several microamperes per square meter, represent the electromagnetic connection between magnetospheric processes occurring thousands of kilometers above and the visible phenomena observed from Earth's surface. As ions from 3I Atlas's plasma tail become incorporated into magnetospheric circulation patterns, they begin to influence the electromagnetic environment that drives auroral activity. The heavy molecular ions, having been processed through magnetic reconnection events and radiation belt interactions, eventually reach the regions of magnetic field convergence where auroral precipitation occurs. Their presence modifies the local plasma composition and electromagnetic wave properties in subtle but measurable ways. The auroral particle precipitation exhibits a complex energy spectrum that reflects the acceleration processes operating throughout the magnetosphere. Monoenergetic electron beams, accelerated by parallel electric fields in the auroral acceleration region, create the most intense and structured auroral displays. Broadband electron distributions, resulting from turbulent acceleration processes, produce more diffuse auroral emissions that spread across wider areas of the polar sky. Heavy ions from the comet contribute additional complexity to these precipitation patterns. Electromagnetic ion cyclotron waves, resonating with the heavy molecular ions at their characteristic cyclotron frequencies, can modify the wave environment in the auroral acceleration regions. These modifications, while subtle, can affect the efficiency of electron acceleration and the resulting intensity of auroral emissions. The presence of heavy ions also introduces new emission lines corresponding to their excitation and recombination processes as they collide with atmospheric constituents. The aurora exhibits temporal variations ranging from rapid flickering on timescales of seconds to slower pulsations lasting several minutes. These variations reflect the dynamic nature of the magnetospheric processes that supply the precipitating particles. Substorm activity, involving magnetic reconnection in the magnetotail and subsequent particle injection toward Earth, creates sudden intensifications of auroral activity that can illuminate entire sectors of the polar sky within minutes. The altitude distribution of auroral emissions provides information about the energy spectrum of precipitating particles. High-energy electrons penetrate deeper into the atmosphere, creating red oxygen emissions at altitudes around 200 kilometers, while lower-energy electrons are stopped at higher altitudes where they produce the characteristic green oxygen line. Nitrogen emissions, appearing as blue and red spectral lines, result from molecular nitrogen excitation and provide additional diagnostic information about the precipitation characteristics. The magnetic local time distribution of auroral activity reveals the electromagnetic structure of the magnetosphere. The midnight sector typically exhibits the most dynamic auroral activity, reflecting the location of the magnetotail where magnetic reconnection and particle acceleration processes are most intense. The dawn and dusk sectors show different characteristics, with dawn-side aurora often displaying more structured arc systems and dusk-side aurora exhibiting broader, more diffuse patterns. Scientists have identified correlations between auroral activity and the orientation of the interplanetary magnetic field carried by the solar wind. Southward-directed interplanetary fields promote magnetic reconnection at the day-side magnetopores, enhancing the transfer of solar wind energy into the magnetosphere and intensifying auroral activity several hours later as this energy is released through magnetotail processes. The ions from 3Y Atlas, embedded within the solar wind carrying these magnetic field orientations, participate in this energy transfer process. Only took photons milliseconds to travel from the collision point in the upper atmosphere down to ground-based observers witnessing the aurora's ethereal glow. Only needed electrons with energies equivalent to a few thousand degrees of temperature to excite atmospheric atoms and molecules into producing visible light emissions. Only required the precise electromagnetic choreography of magnetospheric circulation to deliver these particles along magnetic field lines to the exact altitudes where atmospheric density permits efficient energy transfer through collisional processes. The aurora's response to space weather events demonstrates the electromagnetic connectivity between solar activity and terrestrial phenomena. Coronal mass ejections from the Sun, arriving at Earth as magnetic clouds embedded in the solar wind, can trigger intense geomagnetic storms that push auroral activity to lower latitudes than normal. During such events, the aurora becomes visible from locations far from the polar regions, sometimes reaching latitudes as low as 40 degrees magnetic latitude. The presence of heavy ions from the comet's plasma tail adds new spectral signatures to the auroral emissions that sensitive spectrographs can detect. Mass spectrometric measurements of precipitating ions reveal the isotopic ratios characteristic of interstellar material, distinguishing comet-derived ions from the terrestrial ions that normally dominate the auroral precipitation. These measurements provide direct evidence of the electromagnetic processing of interstellar matter through Earth's magnetospheric system. All sky cameras and meridian scanning photometers continuously monitor auroral activity from ground-based observatories, creating long-term databases of auroral occurrence and intensity. These optical instruments can detect subtle changes in auroral patterns that correlate with the passage of comets through the solar system, providing indirect evidence of electromagnetic interactions between cometary plasma and Earth's magnetosphere, even when the comet itself remains too distant for direct spacecraft measurements. The electromagnetic waves generated by auroral processes propagate throughout the magnetosphere, carrying information about local plasma conditions to distant regions of the magnetic field. These waves, detectable by spacecraft-borne instruments, provide remote sensing capabilities that allow scientists to study the distribution and dynamics of both terrestrial and foreign ion populations within the complex electromagnetic environment surrounding Earth. At altitudes between 80 and 1,000 kilometers above Earth's surface, the ionosphere forms a complex layered structure where solar ultraviolet and X-ray radiation ionize atmospheric gases, creating a plasma environment that exhibits both terrestrial atmospheric properties and space plasma characteristics. The ionosphere's electron density varies dramatically with altitude, solar activity, season, and local time, reaching peak densities of several million electrons per cubic centimeter in the F2 layer around 300 kilometers altitude. This ionized region serves as both the upper boundary of Earth's neutral atmosphere and the lower boundary of the magnetospheric plasma environment. The ionosphere responds sensitively to electromagnetic disturbances propagating down from the magnetosphere along magnetic field lines. When magnetic reconnection events inject energy into the magnetosphere, electromagnetic waves and field-aligned currents carry this energy into the ionospheric plasma, modifying electron densities and creating electric fields that can be measured by ground-based radar systems. These electromagnetic perturbations manifest as variations in radio wave propagation characteristics that affect communication and navigation systems worldwide. As the solar wind, now carrying ions from 3I Atlas's plasma tail, interacts with Earth's magnetosphere through magnetic reconnection and other coupling processes, the resulting electromagnetic disturbances eventually reach the ionospheric environment. The heavy molecular ions, having been processed through magnetospheric circulation, contribute to the population of precipitating particles that deposit energy in the upper atmosphere. Their different mass-to-charge ratios create distinct signatures in the ionospheric response to magnetospheric energy input. The ionosphere's layered structure reflects the altitude dependence of atmospheric composition and solar radiation intensity. The D layer, at altitudes between 60 and 90 kilometers, contains primarily ionized nitric oxide and exists only during daylight hours when solar X-rays maintain the ionization balance. The E layer, around 110 kilometers altitude, consists mainly of ionized molecular oxygen and nitrogen, while the F layer, divided into F1 and F2 regions, contains atomic oxygen ions and exhibits the highest electron densities. Electromagnetic wave propagation through the ionosphere depends critically on the plasma frequency, the characteristic frequency at which electrons oscillate in response to electromagnetic fields. Radio waves with frequencies below the local plasma frequency cannot propagate through the ionospheric plasma and are reflected back to Earth, enabling long-distance communication through ionospheric reflection. Higher frequency waves pass through the ionosphere but experience phase delays and scintillation effects that can degrade satellite communication and GPS navigation accuracy. The ionosphere exhibits diurnal variations as Earth's rotation carries different regions into and out of sunlight, creating a constantly changing pattern of ionization and recombination. The F2 layer density typically peaks in the afternoon local time, several hours after the solar radiation maximum, due to the complex chemistry of ionospheric plasma and the transport effects of electromagnetic drifts and neutral winds. These variations create a dynamic electromagnetic environment that responds to both solar forcing and magnetospheric energy input. Geomagnetic storms, triggered by enhanced magnetic reconnection when the interplanetary magnetic field orientation favors solar wind magnetosphere coupling, can dramatically alter ionospheric structure and dynamics. Storm-time electric fields, mapping down from the magnetosphere along equipotential magnetic field lines, drive enhanced plasma convection that redistributes ionospheric plasma and modifies electron density patterns. The heavy ions from 3I Atlas, participating in these magnetospheric processes, contribute to the storm-time electromagnetic disturbances. The ionosphere's response to particle precipitation exhibits characteristic altitude and energy dependencies that reflect the physics of electron-neutral collisions in the upper atmosphere. High-energy electrons penetrate to lower altitudes where atmospheric density is higher, depositing their energy through ionization and excitation processes that enhance electron production rates. Lower energy electrons are absorbed at higher altitudes, creating layered enhancement patterns that radio wave absorption measurements can detect. Electromagnetic ion-neutral coupling in the ionosphere creates a complex system where ionospheric plasma motion is constrained by collisions with the neutral atmosphere at lower altitudes, but moves freely under electromagnetic forces at higher altitudes. This transition occurs around 200 kilometers altitude, where the ion-neutral collision frequency equals the ion cyclotron frequency. Above this altitude, ions gyrate around magnetic field lines with minimal interference from neutral collisions. Only took solar photons 8 minutes to travel from the sun's photosphere to create the ionospheric plasma through photoionization of atmospheric constituents. Only needed ultraviolet radiation with photon energies exceeding 6 electron volts to strip electrons from atmospheric atoms and molecules, creating the ionized layer that enables global radio communication through electromagnetic wave reflection and propagation effects. Only required the precise balance of ionization and recombination processes to maintain electron densities sufficient for radio wave interaction while preserving the plasma's responsiveness to magnetospheric electromagnetic disturbances. The ionosphere's electromagnetic properties exhibit complex coupling to both the neutral atmosphere below and the magnetospheric plasma above. Neutral atmospheric waves, generated by weather systems and solar heating patterns, propagate upward and modulate ionospheric densities through neutral wind effects and atmospheric gravity wave interactions. Electromagnetic waves from the magnetosphere propagate downward and modify ionospheric electric fields and plasma motion patterns, creating a coupled system that responds to forcing from both directions. Ionospheric irregularities, ranging from small-scale plasma turbulence to large-scale traveling ionospheric disturbances, affect electromagnetic wave propagation and create scintillation patterns observable in satellite signals. The presence of heavy ions from the comet's plasma tail, while representing an extremely small fraction of the total ionospheric composition, can contribute to the growth of plasma instabilities through their modified collision and transport properties compared to the ambient terrestrial ion population. The ionosphere serves as a natural laboratory for studying electromagnetic plasma physics under conditions intermediate between laboratory plasma experiments and the collisionless plasma environment of the magnetosphere. Ion-neutral chemistry, electromagnetic wave-particle interactions, and plasma transport processes all operate simultaneously in the ionospheric environment, creating complex phenomena that require sophisticated theoretical models and observational techniques to understand fully. The subtle electromagnetic signatures of interstellar matter processing through this system provide additional diagnostic capabilities for probing the fundamental physics of space plasma interactions. Behind Earth, stretching away from the Sun like an enormous invisible windsock, the magnetotail extends more than 100 Earth radii into the anti-solar direction, creating a vast cylindrical cavity within the solar wind, where terrestrial magnetic field lines are pulled into a stretched configuration by the constant pressure of the solar wind flow. This magnetotail structure exhibits a complex internal geometry, with northern and southern lobes separated by a thin current sheet where the magnetic field reverses direction and energetic particles accumulate in a hot plasma population known as the plasma sheet. The magnetotail's dimensions fluctuate continuously in response to variations in solar wind pressure and the efficiency of magnetic reconnection at the day-side magnetopores. During periods of enhanced solar wind dynamic pressure, the entire magnetospheric cavity compresses, shortening the magnetotail and increasing the magnetic field strength within the lobes. Conversely, when solar wind pressure decreases, or when efficient reconnection allows magnetic flux to be stripped away from the day-side magnetosphere, the magnetotail can extend to distances exceeding 200 Earth radii. As ions from 3I Atlas's plasma tail become incorporated into the solar wind flow past Earth, they contribute to the electromagnetic environment that shapes magnetotail dynamics. These heavy molecular ions, with their distinct charge-to-mass ratios, follow different trajectories than the ambient protons as they flow around the magnetospheric obstacle. Some become trapped within the magnetotail's plasma sheet, while others continue downstream in the solar wind, carrying the electromagnetic signature of their interaction with Earth's magnetic field into interplanetary space. The plasma sheet, a thin layer, typically only a few Earth radii thick in the central magnetotail, contains the highest density plasma population within the magnetosphere's tail region. Plasma sheet ions, with energies ranging from a few hundred electron volts to several thousand electron volts, exhibit complex motion patterns as they drift under the influence of magnetic field gradients and electric fields. The presence of heavy ions from the comet modifies these drift patterns through mass-dependent effects that create spatial segregation of different ion species. Magnetic reconnection in the magnetotail occurs episodically in events known as magnetospheric substorms, where magnetic field lines in the current sheet suddenly reconnect and release stored magnetic energy. These reconnection events accelerate plasma sheet particles to high energies and inject them toward Earth along newly reconnected field lines. Heavy ions from the comet's plasma tail participate in these acceleration processes, gaining energies that allow them to penetrate into the inner magnetosphere and radiation belt regions. The magnetotail's magnetic field configuration exhibits a phenomenon known as tail flapping, where the current sheet moves up and down in response to solar wind pressure variations and internal magnetospheric dynamics. This flapping motion, with periods ranging from minutes to hours, creates time-varying magnetic field signatures that spacecraft within the magnetotail can detect. The motion reflects the magnetotail's sensitivity to electromagnetic pressure balance between the solar wind and internal magnetospheric plasma populations. Electromagnetic waves propagate throughout the magnetotail, carrying energy and information between different regions of the extended magnetic structure. Ultra-low frequency waves, with periods comparable to ion gyro periods, can transport particles across magnetic field lines through resonant interactions. Higher frequency waves, generated by plasma instabilities and particle acceleration processes, provide diagnostic information about local plasma conditions and electromagnetic field configurations. The magnetotail lobes contain magnetic field lines that have been stretched anti-sunward by solar wind flow, but have not yet undergone reconnection in the distant tail. These lobe field lines, with their nearly uniform magnetic field direction, trap energetic particles that bounce between magnetic mirror points in the northern and southern hemispheres. Heavy ions from the comet, if they gain sufficient energy through acceleration processes, can become trapped in these lobe regions and contribute to the tail's energetic particle population. Plasmoids, large magnetic structures containing trapped plasma and twisted magnetic field lines, form in the distant magnetotail when reconnection events pinch off portions of the plasma sheet. These structures, typically several Earth radii in diameter, travel down the magnetotail at velocities of several hundred kilometers per second, eventually merging with the solar wind far from Earth. Heavy ions from the comet's plasma tail can become incorporated into these plasmoids, carrying interstellar matter into the distant solar wind. Only took the solar wind's electromagnetic pressure 4.5 billion years to sculpt Earth's magnetic field into this elongated tail configuration. Only needed the precise balance of magnetic tension forces and plasma pressure gradients to maintain a stable current sheet structure capable of storing enormous amounts of magnetic energy for later explosive release. Only required the complex interplay of magnetic reconnection, particle acceleration, and plasma transport to create this vast electromagnetic engine that processes both terrestrial and alien plasma through its extended geometry. The magnetotail's response to the presence of heavy ions from 3I Atlas reveals itself through subtle modifications to the electromagnetic wave environment and particle precipitation patterns. Mass spectrometric measurements from spacecraft in the plasma sheet can detect the isotopic signatures of interstellar material, distinguishing comet-derived ions from the terrestrial oxygen and hydrogen ions that normally dominate the tail plasma composition. These measurements provide direct evidence of interstellar matter circulation through Earth's magnetospheric system. Magnetic field stretching in the magnetotail stores energy at a rate proportional to the square of the magnetic field strength, creating a vast reservoir of electromagnetic energy that can exceed 10-15 joules during extended periods of southward interplanetary magnetic field orientation. This stored energy, when released through reconnection events, powers the aurora, energizes radiation belt particles, and drives electromagnetic perturbations throughout the entire magnetospheric system, including the acceleration and transport of heavy ions derived from ancient cometary ice. The magnetotail's interaction with the solar wind creates a complex wake structure downstream of Earth, where the properties of the solar wind plasma remain modified for distances exceeding the magnetotail's length. Heavy ions from 3I Atlas, having been processed through magnetotail dynamics, eventually rejoined the solar wind flow in this wake region, carrying with them the electromagnetic signatures of their interaction with Earth's magnetic field as they continue their journey toward the outer solar system and eventually back into interstellar space. In the central region of the magnetotail, where magnetic field lines from the northern and southern lobes converge, lies the plasma sheet, a thin layer of hot, dense plasma that serves as the primary reservoir for energetic particles within Earth's magnetospheric system. This sheet, typically measuring only 2 to 4 Earth radii in thickness, but extending across the entire width of the magnetotail, contains plasma with temperatures reaching tens of millions of degrees Celsius and particle energies spanning from hundreds of electron volts to tens of thousands of electron volts. The plasma sheet exists in a state of delicate electromagnetic equilibrium, balanced between magnetic pressure forces that would compress it and thermal pressure that resists such compression. The thickness of the plasma sheet varies dramatically in response to magnetospheric conditions and external forcing by the solar wind. During quiet periods, when magnetic reconnection proceeds at modest rates and the magnetotail remains relatively stable, the sheet maintains a consistent thickness profile that reflects the balance between particle injection from the distant tail and losses through precipitation into the ionosphere and escape into the solar wind. However, during magnetospheric substorms, when explosive reconnection events release stored magnetic energy, the plasma sheet can expand to several times its quiet time thickness within minutes. As heavy molecular ions from 3I Atlas's plasma tail become incorporated into magnetospheric circulation, they eventually reach the plasma sheet environment through various transport pathways. Some arrive via direct injection during substorm events, accelerated earthward by the electric fields generated during magnetic reconnection in the distant magnetotail. Others reach the plasma sheet through gradual diffusion processes, slowly working their way inward from the magnetotail lobes through electromagnetic drift motions and wave-particle interactions. The plasma sheet exhibits complex internal structure that reflects the competing influences of magnetic reconnection, particle acceleration, and plasma transport processes. The central plasma sheet, located within the current sheet where the magnetic field magnitude approaches zero, contains the highest plasma densities and temperatures. Moving away from this central region toward the lobe boundaries, plasma density decreases while magnetic field strength increases, creating steep pressure gradients that drive electromagnetic instabilities and wave generation. Heavy ions in the plasma sheet follow drift trajectories that depend on their charge-to-mass ratios, creating spatial segregation between different ion species. Protons and alpha particles, with relatively high charge-to-mass ratios, drift more rapidly around Earth than heavy molecular ions like H2O+, CO+, and CO2+ derived from the comet's ionized coma. This mass-dependent drift effect leads to the formation of distinct ion populations with different spatial distributions throughout the plasma sheet volume. The plasma sheet serves as a natural particle accelerator where ions and electrons can gain enormous amounts of energy through their interactions with electromagnetic fields and waves. Betatron acceleration, occurring when particles are trapped within contracting magnetic flux tubes, can increase particle energies by factors of 10 to 100 as magnetic reconnection processes reduce the cross-sectional area of flux tubes while conserving the magnetic flux content. Fermi acceleration, involving repeated interactions with moving magnetic boundaries, provides an additional mechanism for particle energization. Electromagnetic waves pervade the plasma sheet environment, generated by various plasma instabilities and particle acceleration processes. Ion cyclotron waves, with frequencies near the gyro frequencies of different ion species, can interact resonantly with particles and modify their pitch angle distributions. Lower hybrid waves, occurring at frequencies between the ion and electron plasma frequencies, can accelerate particles perpendicular to magnetic field lines and contribute to the complex particle distribution functions observed in the plasma sheet. The plasma sheet's electromagnetic properties exhibit strong correlations with interplanetary magnetic field orientation and solar wind conditions. Southward-directed interplanetary fields promote efficient magnetic reconnection at the day-side magnetopores, leading to enhanced magnetic flux transport into the magnetotail and subsequent thickening of the plasma sheet. Northward, interplanetary fields generally result in reduced plasma sheet activity and thinner sheet configurations, though complex three-dimensional reconnection processes can still inject energy into the magnetotail system. Temperature anisotropies within the plasma sheet create conditions favorable for electromagnetic instability growth. When the perpendicular temperature associated with particle motion across magnetic field lines exceeds the parallel temperature associated with motion along field lines, ion cyclotron instabilities can develop and generate waves that scatter particles and reduce the anisotropy. Heavy ions from the comet, with their different gyro frequencies, contribute to these instability processes and modify the resulting wave spectra. Only took magnetic reconnection events seconds to minutes to inject solar wind plasma deep into the magnetotail and create the hot plasma populations that populate the plasma sheet. Only needed the conversion of magnetic energy to particle kinetic energy to heat plasma to temperatures exceeding those found in stellar coronas, while maintaining densities comparable to those in the best laboratory vacuum chambers. Only required the precise electromagnetic balance between magnetic pressure and particle pressure to confine this hot plasma within a thin sheet structure extending across the entire magnetotail. The plasma sheet's response to the injection of heavy molecular ions from 3I Atlas reveals itself through modifications to the local electromagnetic wave environment and particle distribution functions. Mass spectrometric measurements from spacecraft traversing the plasma sheet can identify the isotopic signatures of interstellar material, distinguishing comet-derived ions from the terrestrial oxygen and hydrogen ions that typically dominate the heavy ion composition in this region. These measurements provide direct evidence of the electromagnetic processing of ancient cometary material through Earth's magnetospheric particle acceleration systems. Plasma sheet thinning events, occurring during the growth phase of magnetospheric substorms, concentrate the sheet's plasma content into increasingly narrow layers as magnetic flux continues to accumulate in the magnetotail. During these events, the electromagnetic current density within the sheet increases dramatically, approaching the threshold conditions necessary for explosive magnetic reconnection. Heavy ions from the comet participate in these current systems, contributing to the electromagnetic stress that eventually triggers substorm onset and the subsequent explosive release of stored magnetic energy. The chemical composition of the plasma sheet reflects the various source populations that contribute ions to this magnetospheric reservoir. Ionospheric oxygen, accelerated upward through electromagnetic heating processes, often dominates the heavy ion composition during geomagnetically active periods. Solar wind protons and alpha particles provide the light ion component, while heavy ions from sources like 3I Atlas add trace populations that carry the isotopic fingerprints of their exotic origins through the complex electromagnetic environment of the plasma sheet's hot, turbulent interior. Across Earth's surface, a network of sensitive magnetometers maintains constant vigil over the planet's magnetic field, detecting minute fluctuations that reveal the electromagnetic signatures of events occurring hundreds or thousands of kilometers above in the magnetosphere. These instruments, capable of measuring magnetic field changes as small as 1 nanotesla, roughly 50,000 times weaker than Earth's main magnetic field record, the terrestrial manifestations of space weather phenomena with extraordinary precision. The magnetometer stations, distributed from polar regions to the magnetic equator, create a global monitoring system that can track electromagnetic disturbances as they propagate through the magnetosphere and couple to the ionosphere below. The magnetic signatures recorded at ground level represent the sum of multiple electromagnetic current systems flowing in the ionosphere and magnetosphere above. Ring current variations, associated with the drift motion of energetic particles around Earth, create global-scale magnetic field depressions that all magnetometer stations can detect simultaneously. Auroral electrojet currents, flowing in the high-latitude ionosphere during periods of enhanced particle precipitation, generate magnetic field perturbations that exhibit characteristic patterns depending on the observer's magnetic local time and latitude. As the electromagnetic influence of 3Y Atlas's plasma tail modifies magnetospheric dynamics through its participation in magnetic reconnection events and plasma circulation patterns, these effects eventually propagate to the ground-based magnetometer network as subtle but detectable magnetic field variations. The heavy molecular ions from the comet, while representing an infinitesimal fraction of the total magnetospheric plasma content, contribute to electromagnetic current systems through their participation in particle precipitation, radiation belt dynamics, and plasma sheet processes. The global magnetometer network reveals the electromagnetic connectivity between different regions of the magnetosphere through the coordinated timing of magnetic field disturbances. When magnetic reconnection occurs at the dayside magnetopause, the resulting electromagnetic perturbations propagate through the magnetosphere as Alfvén waves, eventually coupling to ionospheric currents that ground magnetometers can detect. The time delays between these disturbances at different stations provide information about the speed and pathway of electromagnetic energy transport through the magnetospheric system. Magnetic pulsations, with periods ranging from seconds to hours, reflect the presence of various wave modes within the magnetospheric plasma. Ultra-low frequency pulsations, with periods between 1 and 10 minutes, often result from the resonant oscillation of magnetic field lines loaded with plasma of varying density. The presence of heavy ions from the comet modifies these oscillation frequencies through mass loading effects, creating subtle changes in the pulsation characteristics that sensitive analysis techniques can identify. The magnetic field's diurnal variation, a regular pattern of daily change related to ionospheric current systems driven by solar heating, provides a baseline against which magnetometers can detect anomalous electromagnetic activity. Sudden commencements, sharp increases in magnetic field strength lasting several minutes, mark the arrival of interplanetary shock waves that compress the entire magnetospheric system. These events, often associated with coronal mass ejections from the Sun, create electromagnetic conditions that enhance the interaction between cometary plasma and Earth's magnetic environment. Magnetic storms, the most dramatic manifestations of solar wind-magnetosphere coupling, produce magnetic field depressions that can exceed 100 nanotesla in intensity and persist for days. During these events, the enhanced injection and circulation of magnetospheric plasma creates intensified current systems that magnetometers worldwide record as coordinated magnetic field variations. Heavy ions from 3I Atlas, participating in these enhanced circulation patterns, contribute to the electromagnetic signatures of storm-time current systems. The magnetic signature of substorms exhibits characteristic patterns that reflect the sequence of electromagnetic processes occurring during these explosive events. The growth phase, marked by gradual magnetic field changes as energy accumulates in the magnetotail, gives way to the expansion phase when magnetic reconnection releases stored energy and intensifies auroral activity. The recovery phase shows the gradual return to quiet conditions as electromagnetic energy dissipates through various loss mechanisms throughout the magnetosphere. Ground-based magnetometers can detect the electromagnetic influence of plasma boundaries and current sheets within the magnetosphere through their associated magnetic field signatures. The plasma pores, marking the boundary between the dense plasma sphere and the more tenuous plasma of the outer magnetosphere, exhibits a characteristic magnetic signature when spacecraft cross this boundary. Heavy ions from the comet, if they penetrate into the plasmasphere, modify its electromagnetic properties in ways that may be detectable through careful analysis of magnetic field measurements. Only took electromagnetic waves traveling at the speed of light microseconds to propagate from ionospheric current systems down to ground-based magnetometer stations. Only needed current densities of a few milliamperes per kilometer in the ionosphere to create magnetic field perturbations detectable by sensitive magnetometers on Earth's surface. Only required the electromagnetic coupling between magnetospheric processes and ionospheric current systems to make the invisible phenomena of space plasma physics observable through terrestrial magnetic field measurements. The long-term magnetometer record, extending back more than a century at some observatories, provides context for evaluating the electromagnetic effects of individual events, like the passage of interstellar comets through the solar system. Statistical analysis of magnetic field variations during periods when comets approached Earth's orbital vicinity can reveal subtle correlations that might otherwise be lost in the natural variability of the magnetospheric system. These historical records serve as an electromagnetic archive of space weather events and their terrestrial manifestations. Magnetometer arrays designed for specific research applications can achieve spatial and temporal resolution sufficient to track the propagation of electromagnetic disturbances across continental scales. The Image Magnetometer Network in Scandinavia, for example, provides detailed coverage of auroral zone phenomena with station separations of a few hundred kilometers. Similar arrays in other regions create global coverage capable of monitoring electromagnetic wave propagation and current system evolution with unprecedented detail. The magnetometer network's response to the subtle electromagnetic influence of heavy ions from 3I Atlas requires sophisticated data analysis techniques to separate these weak signals from the much larger natural variations in Earth's magnetic field. Cross-correlation analysis between multiple stations can identify coherent electromagnetic signals propagating through the ionosphere magnetosphere system. While spectral analysis techniques can reveal characteristic frequency signatures associated with the dynamics of different ion populations within the magnetospheric plasma environment. Throughout Earth's orbital neighborhood, hundreds of artificial satellites maintain their precise trajectories through the complex electromagnetic environment of near-Earth space, continuously adjusting their operations to accommodate the subtle variations in plasma density, magnetic field strength, and energetic particle populations that constitute the space weather environment. These spacecraft, ranging from small research satellites in low Earth orbit to massive communications platforms in geostationary orbit, serve as both scientific instruments and technological canaries in the electromagnetic coal mine of the magnetosphere, responding to changes in space plasma conditions with measurable effects on their systems and operations. The satellite constellation experiences the electromagnetic influence of space weather phenomena through several distinct mechanisms. Atmospheric drag, affecting satellites in low Earth orbit below approximately 800 kilometers altitude, varies with thermospheric density, changes driven by electromagnetic energy deposition from the magnetosphere. During geomagnetic storms, when enhanced particle precipitation heats the upper atmosphere, atmospheric expansion increases drag forces on low-altitude satellites, requiring propulsive corrections to maintain orbital parameters and potentially shortening mission lifetimes. Spacecraft charging, a ubiquitous phenomenon in the space plasma environment, occurs when satellites accumulate electrical charge through interactions with ambient plasma populations and energetic particle precipitation. In geostationary orbit, where spacecraft operate within the outer radiation belt during much of their orbit, differential charging can create potential differences of thousands of volts between different satellite surfaces. These potentials can trigger electrostatic discharges that damage sensitive electronics or create electromagnetic interference with satellite operations. As ions from 3I Atlas's plasma tail become incorporated into the various plasma populations within Earth's magnetosphere, they contribute to the electromagnetic environment that affects satellite operations. The heavy molecular ions, with their distinct charge-to-mass ratios and interaction cross-sections, modify the plasma conditions that determine spacecraft charging rates and the intensity of energetic particle bombardment. While their concentrations remain extremely small compared to the ambient magnetospheric plasma, their presence can be detected through sensitive plasma composition measurements aboard research satellites. The radiation environment within the magnetosphere exhibits dramatic variations during geomagnetic storms when particle acceleration and injection processes enhance the energetic particle populations in the radiation belts and plasma sheet. Satellites operating within these regions experience increased radiation doses that can cause temporary malfunctions, long-term degradation of solar panels and electronic components, and permanent damage to sensitive detectors. Mission operators routinely place satellites in safe mode during severe space weather events to minimize radiation exposure to critical systems, electromagnetic pulse effects, generated by sudden changes in the space plasma environment, can induce currents in satellite electrical systems and create temporary or permanent malfunctions. Substorm events, with their rapid reconfiguration of magnetospheric current systems, generate electromagnetic field changes that couple to satellite structures and potentially interfere with sensitive instruments. The presence of heavy ions from the comet adds complexity to these electromagnetic environments through their modified electrical conductivity and electromagnetic wave interaction properties. Global Positioning System satellites, operating in medium Earth orbit at altitudes around 20,000 kilometers, traverse regions where plasma density variations can affect radio wave propagation and introduce errors in positioning calculations. The ionospheric delay, caused by the phase velocity reduction of radio waves propagating through ionized gas, exhibits systematic variations with solar activity and space weather conditions. Enhanced electromagnetic activity driven by magnetospheric processes can create ionospheric irregularities that degrade GPS accuracy for terrestrial users. Satellite-based magnetometers and particle detectors provide real-time monitoring of the electromagnetic environment throughout the magnetosphere, creating a distributed sensor network that can track the evolution of space weather phenomena with unprecedented spatial and temporal resolution. These measurements reveal the three-dimensional structure of electromagnetic disturbances as they propagate through the magnetosphere and provide early warning capabilities for potentially harmful space weather events affecting both satellites and ground-based technological systems. The space-based observational network includes specialized missions designed to study magnetospheric physics and space weather phenomena. The Van Allen probes, operating in highly elliptical orbits that traverse the radiation belts, continuously monitor energetic particle populations and electromagnetic wave activity. The Magnetospheric Multiscale mission employs 4 spacecraft flying in close formation to study magnetic reconnection processes with unprecedented spatial resolution, potentially detecting the electromagnetic signatures of heavy ion participation in reconnection events. Only took decades of space technology development to create satellite systems robust enough to operate reliably in the harsh electromagnetic environment of near-Earth space. Only needed the precise engineering of radiation-hardened electronics, electromagnetic shielding, and adaptive control systems to enable continuous satellite operations despite the variable space weather conditions that can increase radiation doses by factors of thousands during extreme events. Only required the accumulated experience of hundreds of satellite missions to develop the operational procedures that minimize space weather impacts on critical space-based infrastructure. Satellite constellation management involves continuous monitoring of space weather conditions and predictive modeling of electromagnetic disturbances that might affect spacecraft operations. Mission control centers maintain real-time awareness of solar wind conditions, magnetospheric activity levels, and radiation belt dynamics to make informed decisions about satellite operations and potential protective measures. The subtle electromagnetic influence of heavy ions from cometary sources adds an additional layer of complexity to these space weather forecasting challenges. Commercial satellite operators increasingly recognize the economic impact of space weather on satellite operations, with geomagnetic storms causing service disruptions that can cost millions of dollars in lost revenue and premature satellite replacement. Insurance companies and satellite manufacturers incorporate space weather risk assessments into their business models, recognizing that electromagnetic phenomena originating in the magnetosphere can have direct financial consequences for the satellite industry. The future evolution of satellite technology includes enhanced space weather monitoring capabilities and improved resilience to electromagnetic disturbances. Next-generation satellite designs incorporate advanced electromagnetic shielding, radiation-tolerant electronics, and autonomous systems capable of responding to space weather threats without ground-based intervention. These technological advances will enable more robust satellite operations even as the space environment becomes increasingly crowded with both natural and artificial electromagnetic phenomena, including the subtle influences of interstellar visitors like 3i Atlas as they interact with Earth's complex magnetospheric system. As 3i Atlas continues its hyperbolic trajectory through the inner solar system, moving beyond Earth's orbital distance toward its eventual departure from our Sun's gravitational influence, the electromagnetic coupling between the comet's plasma tail and Earth's magnetosphere gradually weakens with the inexorable mathematics of inverse distance relationships. The heavy molecular ions that once streamed from the comet's nucleus, ionized by solar radiation and accelerated by the solar wind's electromagnetic fields, now spread throughout an ever-expanding volume of interplanetary space, their density decreasing as the cube of their distance from the source. The electromagnetic influence of these dispersed ions on Earth's magnetospheric system diminishes correspondingly, following the same geometric dilution that governs the spreading of electromagnetic radiation through space. Where once the comet's plasma tail contributed measurable populations of heavy ions to magnetic reconnection events and radiation belt dynamics, now only trace quantities of this interstellar material continue to reach Earth's electromagnetic environment, carried by the solar wind's relentless outward flow at velocities approaching 400 kilometers per second. The magnetosphere itself exhibits a kind of electromagnetic memory of the interaction. As heavy ions previously injected into radiation, belt orbits continue to circulate around Earth with characteristic lifetimes that can extend from days to years depending on their energy and orbital parameters. These remnant populations, while exponentially decaying through various loss mechanisms, including atmospheric precipitation and electromagnetic wave interactions, provide a gradually fading signature of the comet's electromagnetic influence on the terrestrial space environment. Spacecraft-based mass spectrometers continue to detect occasional heavy molecular ions bearing the isotopic ratios characteristic of interstellar formation environments, distinguishing them from the terrestrial and solar wind ions that normally dominate magnetospheric composition measurements. These detections become increasingly rare as the comet recedes, eventually dropping below the threshold sensitivity of current instrumentation, though the electromagnetic effects of their presence may persist in subtle modifications to plasma wave propagation and particle distribution functions. The auroral displays that occasionally exhibited enhanced emission lines corresponding to the excitation of heavy molecular ions gradually return to their normal spectral characteristics dominated by terrestrial atmospheric constituents. Ground-based spectrographs require increasingly sophisticated analysis techniques to identify the fading electromagnetic signatures of interstellar matter in the auroral emissions. As the flux of comet-derived ions precipitating into the polar atmosphere decreases below detectable levels, magnetometer networks worldwide record the gradual return of magnetic field variations to their baseline statistical patterns. As the electromagnetic perturbations associated with enhanced heavy ion populations in the magnetosphere fade below the natural variability of the system, the subtle modifications to magnetic pulsation frequencies and substorm characteristics that mark the comet's electromagnetic influence on Earth's space environment become increasingly difficult to distinguish from normal magnetospheric variability. The plasma sheet's composition slowly returns to its typical mixture of solar wind protons, terrestrial oxygen ions, and trace populations of other ionic species, as the electromagnetic circulation patterns that transported comet-derived ions throughout the magnetosphere operate with decreasing efficiency due to the reduced source strength. Mass spectrometric surveys of the plasma sheet environment require longer integration times to detect the diminishing populations of heavy molecular ions with their distinctive interstellar isotopic signatures. The ionosphere's response to space weather events gradually loses the subtle modifications that the presence of heavy ions from 3I Atlas contributed to electromagnetic wave propagation and plasma transport processes. Radio wave absorption and scintillation patterns return to their normal solar cycle and geomagnetic activity dependencies, no longer carrying the faint electromagnetic signatures of interstellar chemistry processed through Earth's upper atmospheric plasma environment. Satellite operations experience a slow reduction in the frequency of anomalous electromagnetic effects that could be attributed to the modified space plasma environment created by the comet's influence. Spacecraft charging rates and radiation dose accumulations return to their expected values based on solar wind conditions and geomagnetic activity levels. As the enhanced populations of heavy ions that contributed to electromagnetic phenomena in the satellite environment decay below operationally significant levels, only took the electromagnetic laws governing charged particle motion in magnetic fields to ensure that the comet's influence would fade as predictably as it had developed. Only needed the geometric dilution of ion density with distance and the finite lifetimes of trapped particle populations to restore the magnetosphere to its pre-encounter electromagnetic state. Only required the patient operation of electromagnetic diffusion and loss processes to gradually cleanse Earth's space environment of the foreign chemistry that had briefly mixed interstellar matter with terrestrial plasma. The electromagnetic interaction between 3I Atlas and Earth's magnetosphere represents a temporary perturbation to the normal operation of the planetary magnetic system, a cosmic experiment in plasma physics that demonstrates the electromagnetic connectivity between Earth and the broader galactic environment. The comet's passage through the solar system has provided a unique opportunity to study how foreign plasma populations integrate into and modify the complex electromagnetic processes that govern Earth's space weather environment. Scientific analysis of the electromagnetic data collected during the comet's approach and recession will continue for years, as researchers apply increasingly sophisticated techniques to extract the subtle signatures of interstellar matter from the vast databases of magnetospheric observations. These studies will enhance understanding of electromagnetic processes in space plasmas while providing insights into the chemical and physical properties of material formed in distant stellar environments billions of years ago. The magnetosphere's electromagnetic response to the comet's influence will remain encoded in the scientific literature as a case study of how Earth's magnetic system processes foreign matter, demonstrating the remarkable sensitivity of space plasma physics to trace populations of exotic ions and the electromagnetic connectivity that links our planet to the chemistry of distant stars through the medium of charged particles flowing in magnetic fields across the vast scales of interplanetary space. In the quiet aftermath of electromagnetic encounter, Earth's magnetosphere settles into the familiar rhythms that have governed its operation for geological ages. The alien chemistry from distant stellar nurseries now dispersed beyond detection throughout the vast volume of near-Earth space. The solar wind resumes its eternal flow past our planet's magnetic obstacle, carrying with it only the faintest traces of the heavy molecular ions that once streamed from 3I Atlas's sublimating nucleus, their exotic isotopic signatures diluted beyond measurement in the endless circulation of solar plasma through interplanetary space. The magnetospheric system exhibits the electromagnetic equivalent of geological rest, its various plasma populations and current systems operating within the normal ranges of variability that characterize Earth's space weather environment during periods between major solar disturbances. Magnetic field lines resume their steady convection patterns, carrying terrestrial plasma from the ionosphere to the magnetotail and returning solar wind plasma toward the day-side magnetopores through the cyclic circulation that has operated unchanged for billions of years. The radiation belts maintain their characteristic populations of energetic electrons and protons. The exotic heavy ions from the comet's plasma tail having either precipitated into the atmosphere or diffused outward beyond the trapping regions where Earth's magnetic field can confine charged particles for extended periods. The electromagnetic wave environment returns to its baseline state, dominated by the natural plasma instabilities and particle acceleration processes that generate the chorus emissions, plasmaspheric hiss, and electromagnetic ion cyclotron waves that pervade the magnetospheric cavity. Auroral activity continues its ancient dance above the polar regions, painting the night sky with the green oxygen line at 557, 7 nanometers, and the red nitrogen emissions that mark the collision of magnetospheric electrons with atmospheric constituents. The spectral signatures of heavy molecular ions fade from the auroral emissions, leaving only the familiar patterns of terrestrial atmospheric excitation that have illuminated polar skies since Earth developed its magnetic field billions of years ago. The ionosphere maintains its layered structure and diurnal variations, responding to solar ultraviolet radiation and electromagnetic energy input from the magnetosphere with the same physical processes that have governed upper atmospheric plasma dynamics throughout Earth's history. Radio wave propagation characteristics return to their normal dependencies on solar activity and geomagnetic conditions, no longer carrying the subtle electromagnetic signatures of interstellar chemistry processed through the ionospheric plasma environment. Ground-based magnetometer networks record the familiar patterns of magnetic field variation that reflect the electromagnetic state of the magnetosphere-ionosphere system during geomagnetically quiet conditions. The subtle perturbations that once marked the electromagnetic influence of heavy ions from 3I Atlas disappear into the natural variability of the terrestrial magnetic field, their signatures archived in scientific databases as evidence of a brief cosmic encounter between worlds separated by deep time and vast distance. Satellite systems resume their normal operational parameters, no longer experiencing the modified electromagnetic environment that briefly accompanied the comet's influence on magnetospheric plasma populations. Spacecraft charging rates, radiation